actually works.
Thank you very much for the introduction. I'm Kevin. I'm part of the Cyber Grand Challenge part of Shellphish, and I will be talking about the experience that we had, essentially just starting with a little bit where Shellphish is coming from, which kind of spurs the entire why we participated in it. Shellphish was essentially born at the University of California, Santa Barbara, and the Sec Lab there, which is led by two professors, which is Giovanni Vigna and Christopher Krugel. Some of you might know both of them, some of you might either one of them. And all of us there are essentially academics at heart. So on the left side there, you have Giovanni like 15 years ago, still with long hair. And then on the right side, you have Chris. And Shellphish, I mean, only a few of you might know, is actually in Santa Barbara, which is a very nice city in Southern California at the beach. If you look very closely, this is where Shellphish was born and still is, and which is also why our tagline is essentially Hex on the Beach. Shellphish started in 2004 with just Giovanni and a bunch of his grad students. So a few of you might know Balzaroth, which is Davide Balzarotti from Eurocom, and then you have William Robertson, who is a professor at Northeastern. Both of them are also academics at heart. Starting from there, essentially, Shellphish just took its life and went on to win DEF CON CTF in 2005, which is also the only, essentially, time at which point Shellphish won. We have qualified for DEF CON CTF every year since then, I think, but 2006, but we've never actually won after. So we're really good at qualifying, but we're also really good at not winning, which, well, the Cyber Grand Challenge also kind of showed. Shellphish from then essentially evolved over the years a little bit longer. So some people moved to Vienna and then essentially hired some grad students there. And then they moved back to essentially Santa Barbara. And then a few more people started to move around. And then at one point, a lot of students got interested in it when essentially Santa Barbara started to organize the ICTF that some of you might be familiar with, essentially the International Capture the Flag contest, which we usually aim to organize once a year, but if you've actually paid attention in the most recent years, doesn't actually happen that often anymore. Going on from there, essentially, you just have like more people moving and moving, some people essentially going on and getting a real job, and then essentially more people just kind of coming and going, and the core part now essentially is moving very much to like less people, but more concentrated to Santa Barbara. You still have like a bunch of people at Northeastern or Boston or in London or Arizona or Eurocom. And essentially from there, Shellphish just essentially goes on and on and on. Coming to the Cyber Grand Challenge, which is the actual topic, but I just wanted to give you a little bit of essential information that Shellphish is, at this point, I think, the longest running CTF team that exists, but also that essentially there's a lot of fluctuating of people, so it's not that the core people are still all there, it's just a bunch of people of them are still there. Some of you might not be familiar with essentially DARPA in general, so DARPA is essentially just the research part of the US military. So you have it's a defense research project agency, so Defense Advancements Research Project Agency. Essentially, they aim to fund fundamental research in a variety of different topics that touch military application, not necessarily right now or in the next 5 years, but essentially down the line in like 15, 20 years. And that all essentially started with DARPA Grand Challenges for self-driving cars, which essentially were held first in 2004 and 2005, and the first one actually, no car actually finished. And then only in the second time they organized it, I think a year or 2 years later, self-driving cars were able to essentially make progress and finish essentially from start to finish within 7 hours for 130 miles, so almost like 200 kilometers, which at that point, yeah, it's like 30 kilometers an hour. I don't think you want to actually be sitting in a self-driving car going on the highway at like 30 kilometers an hour. But since then, I mean, a lot of you probably have seen the news on like Google, Uber, all of them essentially have now fielded self-driving cars, at least in California and in Pittsburgh. And similar to that, you essentially had like the Robots Grand Challenge, which kind of aimed to essentially fund robotic research that goes on to, like, of course, into military applications, but also essentially household support, these kind of things. And to essentially spur a similar kind of research, DARPA organized the Cyber Grand Challenge, and then there the goal was not to essentially build a robot that helps you at your household chores, or build a self-driving car so you can read the newspapers actually while you're sitting in the car commuting to work. But the idea was to have a project that works on software to find vulnerabilities in them automatically, patch them, and generate an exploit all automatically without any human involvement whatsoever. So essentially you start by just getting a binary, take that binary, analyze, find flaws, and essentially generate a program that exercises those flaws to get full code execution. And the timeline for us, at least for the DARPA Cyber Grand Challenge, was essentially where you see the very first CGC flag. This is when the application for the funded track by DARPA opens. So essentially you have the option to write a grant proposal and to apply for funded track with DARPA, and then you essentially get money essentially every quarter, every year, to fund the research that goes into the Cyber Grand Challenge, your participation into the Cyber Grand Challenge. We actually decided not to do that because we're just too busy with other research. So none of us wanted to do the commitment of, now we have to participate in this. And then there was, later on, there was with the registration deadline shortest, essentially. Then we signed up very briefly, like 2 days before, when there was the open track, so where you're not actually getting any money, but you only essentially are allowed to participate if you want to. So essentially, it's all, you have to fund it, and then you have to figure this out. And from there, we essentially started to take this very much in Shellphish spirit by procrastinating as long as possible, and then trying to rush this on the last minute, which for the first scored events didn't really work out. Luckily, the 2 scored events in the very beginning didn't actually matter for qualification. But they were just there so that when you're on the funded track, you can verify that your system works, so you're not actually being kicked out of it and have to possibly give money back. And then around, before the actual quals showed up, 3 weeks before, we actually started, yeah, oh shit, we should probably start doing something, because we don't want to be embarrassed in front of everyone. I mean, there's somewhat of a name associated with Shellphish, so we didn't want to essentially embarrass the brand behind it. So we just spent like 3 weeks of pretty much insanity, 14 hours a day working for like 10 people every day, just to essentially get something to run that works and that we can at least field for the qualification to possibly make it. And much to our surprise, we actually made it in the top 7 teams that qualified. For us, it was really just, okay, let's be sure that we're not looking like idiots, but worked out fine. In the same spirit after, we just didn't do anything for like 9 more months, even though we got $750,000 US dollars from DARPA to essentially pay us to do it. But we was like, we're good. We just wait a little bit. And then like 3 months before that, we essentially, yeah, okay, maybe it's time. We're not allowed to touch any of the software that we are developing at the final event. Everything has to be completely autonomous, and machines might fail. I mean, if you're getting 64 machines with 2 disks each, the likelihood that one of the machines fails in a 10-hour interval starts to get fairly high, and you start to freak out. It's like, ooh, what if this is my database? What am I going to do then? So you're really starting to think about resiliency and essentially failover, which is surprisingly difficult, particularly if you've never done this. So essentially you start reading a lot of documentation and start to figure out like, oh yeah, this doesn't really work as much as I thought it would. And then, yeah, so we had 3 months of insanity with a bit more people, sometimes essentially switching from like sleeping during the night to sleeping during the day because there was just too much work to do. And then, as usual, we essentially committed the last change 2 hours here, as I think about 2 hours before we lost access to it. It's like, why not live dangerously here? This is the team that actually participated. So these are the only people that are involved. Now there's actually, I think, 2 people missing that are involved with the CGC from Shellphish. So Shellphish in general has like 35-ish people, but these were the people that were involved with the CGC part of it, which are actually, interestingly, not primarily American, but it's a fairly even split between American and Italians, and 1 German, 1 Indian, and 1 Chinese. Some of you might have seen some of them actually around at other conferences in Europe, for instance, at CCC, a bunch of those people usually show up. Going from there, essentially, looking at what do you have to do for the DARPA Cyber Grant Challenge, essentially, what does your system have to do that you're developing? And there's essentially three things. First, you have to analyze the binary that you're getting. Of course, you have to pwn the binary that you're getting, otherwise you're not being able to generate an exploit for it. And of course, DARPA has also like the defense part as their goal, because they probably want to defend against software that they might be running on their network, but for which they're not able to get essentially the source code. And looking at the analyzing part, so DARPA made this a little bit easier. If they would have run this on Windows or, for instance, on Linux, this would have been essentially a nightmare from the engineering effort, simply because if you just think about what you would need to implement the POSIX API almost truthfully in an analysis system, I think every one of us on the team would have said, like, yep, no, we're not going to do this. Like, there's a practical impact, of course, there, but from a research point of view, it's simply not as interesting. And to essentially remove that part from the equation, DARPA came up with their own operating system, which essentially has only 7 syscalls, which is transmit, receive, there's the FD wait for select, you have an allocate and deallocate to essentially manage memory on the heap, then you have random, which is also your only source of randomness, and then you have terminate to exit gracefully. On essentially the pwning part, you have noticed that there's no actually open or read or write for the file system, because there's no access to the file system for the challenges that they're running. And for the normal CTF, you would just read challenge directory /flag. That, of course, doesn't work here. So they decided to have different definitions of what actually exploiting means. And for the qualification, it means, so the qualification round, which was around a year before the final event, it meant that if you crash the program, you essentially show that you have control over it. Which, of course, in practice is not true, right? I mean, we all know that just being able to crash it doesn't mean that you can essentially get full control, program counter at control, right? And then essentially, if you go on to the finals event, they started to essentially have 2 different types of exploits. There's type 1, which is essentially you're overriding the flag. So the idea is that you just set a register to a specific value, and then you crash at another address. And then you show that with this, you essentially have control over the program. And as a second type of vulnerability that they wanted to show is that essentially you leak from a specific flag page in memory. So you have a flag in memory that is filled with random data as soon as the program starts. And then if you're able to leak 4 consecutive bytes of that, you essentially show that you have a proof of vulnerability for that specific type of exploit. And of course, in addition to that, you essentially have patching. Of course, you could just step out everything, right? You could just remove everything, and then stuff doesn't necessarily work anymore, so they have functionality checks that fail. Similar to that, of course, you could start adding a signal handler that every time it crashes, you just, yeah, fine, I'll just call exit, then it doesn't crash anymore, which actually some teams did for the qualification event. So it just registered, essentially, so they made it slightly different. By essentially not registering signal handler, because that doesn't work, because there are actually no signal handlings on the decree operating system. But what they did, essentially, they added a detour before that essentially makes sure is the memory allocatable, readable or not. And there's a few tricks that you can use by the 2 system calls that exist. So if the memory is allocated, you just essentially jump back, and if it's not allocated, you essentially exit an instruction before. So the program counter is not actually under control. And of course, on top of that, you essentially can do more fully fledged solutions that essentially you just do full control flow integrity checks. But of course, they're having performance penalties. I mean, you cannot just run something that gives you 100% overhead. In practice, you cannot. And for the DARPA Cyber Grant Challenge, they also decided not to. And so for this, we essentially implemented the mechanical fish as a play on the mechanical Turk and fish, which is the name of the Chinese guy on our team. And the full system essentially needs to patch, find crashes, and exploit those crashes of every binary. And just to give you a little bit of more background on the DARPA Cyber Grand Challenge, it was organized as a standard CTF where essentially you have a referee in the middle and you have 4 different teams around it. And the DARPA Cyber Grand Challenge just takes all the humans out of that loop and replaces them with machines that are fully autonomous. And they actually had the certified air gap, which was certified by, I think, West Point Academy military personnel. And then they essentially, on top of that, to export data out of that air gap, they had 2 robots, which one is backup and one is essentially to actually burn a Blu-ray, which is then transported with a robot over the air gap and then being read in again. There's an interesting video of that on YouTube if you want to check it out. And in case both of the robots failed, they actually had a West Point cadet who would have just had to walk between and transport a Blu-ray. And looking at the final event, the CGC final event, it was divided into 96 rounds. Each round was usually, rounds essentially in which scoring happens. And each round had a short break in between them, which was used to essentially do all the scoring calculations. And since there's no way that a human is involved, they essentially had an API access for your CRS. So you had to write a component that automatically talks to their API, extracts the challenge binaries. So challenge binaries and challenge stats are the services that you're running. And then you essentially have to analyze those. And after every round, they decided to score for each round, for each team and servers. And the score was calculated by essentially availability times security times evaluation, where availability was essentially performance. So is your binary still working well? Does it pass all the functionality tests? If so, what is the performance overhead of it? Then there's a question, did other teams have exploits? If so, was your binary successful in patching against them? So essentially, if you deployed a patch, was it able to actually withstand the exploits of other teams? Or were you only able to essentially withstand 5 exploits, but there was another one. One team analyzed your new binary and found another vulnerability that you might have not found yet. And then on the third part, you have the offensive score, which is essentially how many teams were you able to exploit with any exploits you might have fielded against them. And of course, designing such a system gets really, really complex. So at some point, I think none of us actually knew how the database was looking anymore. So we started to write everything down by hand to essentially retrace our own steps, because it was 3 weeks of insanity. And there essentially you have like a bunch of challenges and which kind of patches we were actually able to generate from them. And of course, DARPA wanted to encourage essentially really well engineering efforts to essentially, yes, you should probably code freeze your code, and you should probably test it quite a bit. And of course, that didn't really work for us, because research is hard. We're not really taking this too seriously. We really tried to, but it just didn't work. So I think after our code freeze, we had like another 120 commits roughly per component, because why not live dangerously? So these kind of things happened, which are very meaningful commits, like, yeah, let's fix this. And Francesco asked for some forgiveness. Although it passed the test, obviously. I mean, if you look here, it actually passed the test. And then if you look a step closer, this is actually in Vegas in the suite that we had. And you still have like 5 people hacking on code, like 15 hours before we lose all access to the infrastructure. And then there's essentially just, it has to work if the machines boot up. And looking at essentially the mechanical fish, it has a bunch of different components. All of them but Farnsworth are actually stateless insofar as that if you take down the machine that it's running on, it's migrated gracefully to a new machine and takes over all the responsibilities. I will go into a little bit of detail into Meister and Farnsworth and some of the worker components. Just to give you an idea, Ambassador is essentially the only component that is able to talk to the DARPA API, so it's the TI API, which is where you're getting information about scores, information about rounds, information about other teams, and then it passes that on to our database, which is Farnsworth. Scriba is the component that makes our decisions on like the game theoretical part of the CGC, essentially what patches to submit and what exploits to launch against which team, depending on what they might have fielded, so what services they might be running. And specifically, Farnsworth is essentially not only the database, but it's more an object relational model around it, which answers the questions like what challenge stats have been fielded, so what services are in play. Because if services are in play at one point, they're going to be, they might be defielded at a later point, and then they're never coming back. So at that point, you can stop analyzing everything for that specific service so that you can use the computational resources that you're given, with the 64 nodes cluster that they were giving you, to essentially work on other challenges. And of course, this is like, you have to start coordinating these 64 machines that you have so that you're using them actually to a really large degree. And this also takes a good amount of effort. For that, we essentially started to implement a component on top of Kubernetes, which essentially allows you to run containers, which some of you might be aware of, which essentially just looks at the game state, and then it asks each creator for each different kind of worker. So for instance, you have the poll creator, you have a tester, you have patcher Rex, which is there to generate patches, you have Rex, the POV fuzzer, and color guard, which are all offensive components. And each of them has their own creator, which decides should this specific job or this specific task run at this specific point in time. And this is exactly what the Meister is doing. Every creator assigns a priority. For instance, if you had to have a lot of crashes for a specific service, you might want to essentially work on this, on exploiting those crashes rather than finding new crashes, because you first should triage them to figure out if any of them are exploitable or not. And this is exactly what Meister does. It decides, should we find a new crash for this service? Should we create a patch for it? Or should we try to find an exploit for it? And of course, as usual, this is the component that got the last minute changes. Around 2 hours before we lost access, we started committing and adding new features. And if that would have gone wrong, I think, yeah, the mechanical fish would have just not lived on. It would have just crashed and burned. Another thing I need to mention is Anger. Anger is essentially the core of all the worker components that we have. I'm not sure, a bunch of you might already be familiar with Anger is. Anger is essentially a binary analysis framework, which you can use for a variety of different tasks that you might want to perform on a specific binary to analyze it. It's based on, right now, the intermediate representation is used as VEX. So essentially everything that's supported by libVex can be lifted into Anger and analyzed there. It's open source. It's developed by a bunch of students, most notably Jan and Fish from UC Santa Barbara, and they made it available under an open source license, BSD to be precise. So you can actually use it for commercial use if you desire so, without running into the standard licensing issues that you otherwise might have with GPL. The core idea behind Anger is essentially that you just take it and that you start replacing parts, different components of it, and then you essentially get different kind of analysis techniques. So for instance, you might just start out with concolic execution as the one analysis technique that you have, or you might want to go into combining different parts of Anger to do automatic exploitation, or you might even want to use it for patching. And this is precisely what essentially we used Anger for. So we wrote different components that are all based on Anger, that use Anger slightly differently to essentially perform the goal that we want to do: automatic exploitation, patching, finding leaks, all these kind of things. And to actually find crashes that you then might be able to use for it to generate an exploit, we started to essentially depend on fuzzing, which, if you're not aware what fuzzing is, it's essentially just sending a bunch of different kind of input to a program and see whether it crashes and burns or not. And there are, of course, different research questions that you need to answer in the respect of fuzzing. What inputs should you use? How do you generate inputs that are actually valid? So for instance, if you would like to fuzz a web browser, There are a lot of inputs that you could generate, but probably 99.999% of them are not even interesting because they're just plain text without any parsing involved. And we essentially started to find a variety of different crashes, from network traffic that DARPA provided to us. Then we started to find crashes with symbolic execution, which is really heavyweight. So you have having a lot of trouble to essentially do this at scale. And then there's also fuzzing, which is very easy to do at scale, but where you might run into problems otherwise. And we depend for fuzzing on American Fuzzy Lob, which I'm sure also a lot of you are familiar with. So I'm just going to skip over this fuzzing part. But here, for instance, you have a problem where AFL in general is not necessarily really efficient. So as soon as you start to get magic values involved, for instance, a check that's in the beginning, or essentially the header that might be there, AFL is not necessarily. There are some tricks that you can use, but AFL in general is not really efficient there, because simply the space of different kind of solutions that you can put in for X, if it's, for instance, a 32-bit or 64-bit value, is just too large to find this at random. So you might try a bunch of them, and then at some point, you still haven't actually found the actual path to win. And this is exactly where anger comes in. So the symbolic execution part, for instance, you might decide that this essentially, like, you start adding constraints if you do symbolic execution. So what symbolic execution is essentially whenever there's user input, you essentially start adding constraints to the state of the program that you have, so that essentially the state depends on the user input. But the user input is actually symbolic, and there's actually not really any value associated to it. And then you get this kind of these path conditions that you want to go, for instance, to the you win part. Then essentially you would have to look at this specific path. These are the path conditions that you came up with when you traced print you win. You essentially first have the condition that you need to path x is greater or equal than 10, or second you have x modulo 1337 equals 0. And this is exactly the kind that anger starts to shine. So essentially you have these path conditions, and then you start asking your solver, in our case that's these three from Microsoft Research, to essentially what are the path conditions, what is the solution to the path conditions that I have so that I actually reach this state of the program. And in this case it will tell you the input that you have to provide to actually reach the you win state. You have to provide as input for x equals 1337. And the combination of AFL and anger was published in a research paper at NDSS 2016, so this year, which is essentially combining those two in a feedback loop. So you combine fuzzing with symbolic execution. And for instance, if you look at the following CFG and you just start with like cheap fuzzing coverage, for instance, that might AFL give you, so you run AFL for a bunch of times, and then you essentially get the two inputs x and y that essentially trigger the left and the right path at essentially this branch. But you still have this specific part of the program that is unexplored and where there might be a crash or vulnerability, so you want to go there. And this is where this dynamic symbolic execution part comes in. So essentially you try to ask, like, how do I get to this specific part? And then you have the CGC_magic, which is then being fed into essentially AFL as a new test case. And then essentially AFL might find new other cases, for instance, CGC_magic Y. And with that, you essentially have a feedback loop, and you start looking into the symbolic execution, which is this really heavyweight solution to a similar problem that fuzzing solves, only as soon as the fuzzing part is essentially stuck and doesn't get along anymore. And to essentially go from a specific crash to an exploit, you essentially have to do automatic exploitation. So if you look at, for instance, at this specific code fragment, the vulnerability is a simple buffer overflow on the heap. So essentially in the while loop, you're essentially overriding possibly the function pointer in the structure component. So first you essentially start by just getting some kind of input, and then essentially the heap looks as just being filled with symbolic bytes in memory, so I just walk over. And then if you look at how this looks for anger, it's just going to be the compare do something with 1 essentially looks for anger as a call to a symbolic byte. And then at this point, you essentially know you have control over the symbolic region, so you essentially can specify where you want to call. So you have control over the PC at that point. And starting from there, you essentially, if you have control of the PC, so essentially you have this essentially is the symbolic assertion, the assertion that the PC is actually symbolic, then you can just go on and essentially make sure that your shellcode fits into memory. Then you constrain the path that you want to go to, so that you have a region in memory that's large enough for the shellcode that you want to execute. So that in number 2 in the first line. In the first 3 lines, and you essentially use that. So the BVV is just a byte vector. It's just an implementation detail, but it just makes sure that your shellcode is in memory and that you know the address where it's on. And going from that, essentially, you just add a constraint that the program counter at this point should point to the buffer address where your shellcode lives in, and then you just dump this entire thing, and then you have the input that you can use to essentially get an exploit for crash. This is, of course, overly simplified, and there's a lot more research going on, and it doesn't necessarily work in all cases. But there's a lot of things that the CGC also made significantly easier with their operating choice. And so, in conclusion on the automatic exploitation part, you just need 3 components, which is essentially a symbolic state that's vulnerable, where you have control over the PC. And then you just need to be able to add some constraints to essentially be able to put the shellcode into the address space. Of course, if you're doing ROP, this is a little bit different. And then you essentially just need to be able to constrain the PC to point to the shellcode. And we used in the CGC a bunch of different components. So we had circumstantial exploits, which are targeting type 1 exploits. So in a type 1, you essentially just have to crash at a specific address, and before that you have to set a specific register to a specific value. Both of those 2 things you essentially agreed on beforehand with the challenge infrastructure. But if you note that this does not actually require you to execute shellcode, because if you might have control over a specific register already, for instance, through some kind of residual data that you might have put in, or something that depends on a computation that you have done. So you might be able, if you deduce that computation, for instance, through symbolic execution, you might be able to set that specific register without actually having to have control over the PC. And then you need the control over the PC to essentially jump there. But you do not need to essentially be able to leverage that to go on. So it might be enough that you can set a few bits of the PC to get a circumstantial exploit. Then, of course, you have the standard shellcode exploit, which primarily works because by default, there's no stack protections enabled, which is, of course, an easy thing for every competitor to essentially enable immediately, make the stack not executable because none of the challenge sets actually depend on it. But still, some teams did not do it immediately, so you still were able to leverage a specific window to essentially use shellcode exploits. And then, of course, you have the standard raw part, which is essentially just getting return-oriented programming exploits, which is also open source, as the rest I will talk on later. On top of that, you have essentially goals that target type 2 exploits, which is essentially an arbitrary read. For instance, you might be able to read specific bytes from the flag page, but you might not actually be able to get control over the PC. And then you essentially have 2 other kinds of exploits, which are more complicated. So, for instance, read-write exploration, you might essentially be able to lever these in 2-stage exploits, or you might be able to override a vtable pointer. And looking, for instance, particularly at type 2 exploits, where you just need to leak specific information, we there have color guard, which essentially makes sure that you're looking at flag page leaks. So the way it works, essentially, it just runs everything in anger, and the only thing that's treated as symbolic is the memory region where the flag page is. Everything else is being taken from different test cases, and then at the very end is being checked, is any of the output that was given on standard out symbolic? And at that point, if it's yes, you know that this is actually an input that leaks part of the flag page, and you can now control it. Or if it doesn't, you know that this specific input does not leak the flag page and cannot leak it at all. And interestingly, this actually solved one of the challenges at the DEF CON CTF, I think within 30 seconds of it actually popping up. So essentially within 30 seconds, the challenge popped up. The CRS essentially got it and then solved the challenge and submitted an exploit. And of course, the last step next to exploiting was patching, for which we had patch-RX, which essentially starts by applying a bunch of different patching techniques. For instance, you have stack randomization, you start encrypting the return pointer, you essentially start checking what are you transmitting. For instance, are you sending out more than 4 bytes of the flag page? That if yes, do not send out more than 3 bytes of it. Instead, terminate immediately, because the likelihood that this is going to be a type 2 exploit is really, really high. Or other things we essentially looked into are adversarial patches to essentially use them to disrupt what a specific analysis software might be trying to do on your kind of patch. So for instance, another team is running something in QEMU, you might want to essentially disrupt the functionality of QEMU. Similarly, if somebody is running this in PIN, you might want to try essentially attack PIN. And with that, the patches essentially either inserted data or code. So for instance, code inserted that we might was essentially make sure that stack variables are zeroed out as soon as they're allocated, but before they're used. So that is essentially so that you're not leaking anything that might have been put there into the same memory region by, for instance, a previous call. And to actually implement this, we had 2 different, hindsight actually 3 different techniques. So one is a standard detour, essentially that you jump out where the interesting code part is, and then at the later point you just jump back. But on top of that, we also essentially, Fish in particular, implemented a reassembler that essentially completely disassembles the binary that you're getting and starts to look into using specific pointers that might usually be troublesome or being deduced through the symbolic values. And since we noticed that most of the binaries are actually compiled with -0, Fish also implemented a bunch of optimizations on the binary. So for instance, constant propagation or dead store elimination, and also making sure that you're not unnecessarily copying variables from your current stack into possibly the local stack when you're doing a call. All of these kind of things he optimized in a way which actually led to some binaries performing better with our patches than before. Some of the adversarial patches we looked into are, for instance, to detect QEMU. So this one essentially just, if the mantis of an 80-bit float is set to 0 in user mode at an older version in QEMU, it just started to crash, which actually led to the visualization of the CGC people, because they were running this in user mode QEMU, actually crashed. So the entire, essentially they visualized every specific part, like every instruction of it, and at this point it just stopped. Other adversarial patches are essentially just transmitting the flag, but on standard error instead of standard out. Essentially, as soon as the program loads, you just dump the entire flag page to essentially standard error, which might trigger some analysis techniques to consider this essentially as a binary that might possibly have a backdoor or essentially might have a problem, these kind of things. So essentially, throw off analysis systems of your opponents to figure this out. And then we also came up with a backdoor in our patches. So all our patches included a backdoor that we could use to essentially execute code and essentially get whatever we needed to do. It was a standard hash space challenge response backdoor. It was not cryptographically secure because you also have to be very careful in the performance penalties. So we looked into some of them that would have been cryptographically secure, but it's just simply not practical for essentially the DARPA Cyberman Challenge. When you start having too much of an overhead, you're being essentially hurt by the performance penalty that your backdoor introduces, even though it's rarely actually being executed. So we came up with something that you can easily pre-compute offline, but if you haven't done this before, it's just too difficult. So you can derive the symbolic formula that you need to, and you could theoretically embed this in exploits, but the time that you need to actually solve the symbolic formula is higher than the execution timeout that you can use on the DARPA Cyber Grand Challenge infrastructure, because they were running the exploit for you. As said, we have some other generic patches like return pointer encryption. We're protecting indirect calls and jumps. Essentially, so they, instead of crashing at a specific address, as soon as we have a call or a jump, where the value is not a constant, but possibly derived from user input, we essentially insert a stub in which we're first trying to read from that address, which means if the address is not allocated, we actually crash before at the current instruction, which means that if a team throws an exploit at us that does exhibit this specific behavior, the exploit is not counted as successful because they're crashing one instruction too early. And then we also extended allocations on the heap by just a random amount of bytes every time. So every time you allocated something, you just get a few more bytes of space, which threw off some of the patches that depend very heavily on the amount of space that, for instance, a heap allocation takes up. The same goes on for the stack, and as I said, you might have variables on the stack that might have been set up from a previous call. And looking at the actual CFE, so Mayhem won actual first prize. Xandra, which was from TechX, won second prize. Both of them were funded teams. So both Mayhem and Xandra essentially applied to get a grant from DARPA in the beginning to be funded, so being paid to actually do the research. We have not. We ended up being third, and if you actually see the huge drops that we had in, I think, availability, you notice that some of our game theoretical techniques were not actually the best ones you could have chosen. Interestingly, there are only 2 academic teams in there, or 3, I think 3. Shellphish, Galactica, and GEMA, as far as I know. And the Galactica is from UC Berkeley, which is really great for us because we can essentially now point to them, yes, but we won this one, because you have like this rivalry between UC Berkeley and UC Santa Barbara. Looking at essentially strategies and techniques that we did used at the CFE was essentially we decided to not evaluate our own patches, even though performance really could hurt us. And that was primarily because when we tried to, it was simply too unreliable. Essentially, the infrastructure that DARPA used to evaluate your patches was so vastly different from anything else that almost all of the other teams could come up with that there was no point in trying to. We also decided to not deploy any network rules. So you have the option to deploy network rules to essentially prevent specific traffic from actually reaching the binary. The problem there is that every network rule is being applied to all binaries, so to all services. So if you have one error in a single network rule, you're losing availability for all services, which means you're losing points for all services. And I think all but 1 or 2 teams noticed that in essentially the tests that DARPA organized, and all of them decided to not deploy network rules. Also, because we were deploying adversarial patches, we made sure not to analyze other binaries in essentially our heavyweight solutions, because we were assuming that similar to us, they would have adversarial patches and would try to aim to get our analysis techniques to essentially fail, stall, or take up a huge amount of resources. Unfortunately, we decided to deploy our patches immediately, which actually hurts you because you're getting 1 round of downtime for the deployment of the patch. And we started to look a little bit into how much points that actually cost us. And although we're not 100% sure, we think that it at least cost us probably at least 5,000 to up to 17,000 points, which might have made the difference between second or possibly first. But of course, Mayhem also essentially got stuck in round 49. So you have no idea how it actually would have ended up. And on the offense part, we essentially started to just pwn as much as possible as every other team also. Was not really any drawback in holding back your exploits, which you might have had if you have like a human CTF, where sometimes you might only want to throw the exploit at specific teams because you know this other team is just really quickly going to look at this your exploit and is able to reproduce it and throw it against other teams, patch their own binary. So you might want to selectively throw your exploit in a human CTF. For instance, you might not want to throw it against the top 2 teams, the top 3 teams. But in the Cyberground Challenge, that doesn't necessarily apply because every essentially opponent was a machine. Overall, 82 challenge sets were fielded, so different challenges. Some of them they're all trying to mimic applications that you would find in the real world. So for instance, some of them were full web servers that essentially spoke HTTP1, other were full SMTP servers. Some of them were running over multiple binaries, so you had interprocedural IPC calls between them. And for these 82 challenge sets, our cyber reasoning system, Mechanical Fish, generated a total of 2,442 exploits, of which only 1,709 were actually fully reliable, so they worked every time you actually tried them. And we generated exploits for 14 out of 82 of the challenge sets, and the longest one contains about 4,000 lines of C code, which most is essentially setting up symbolic formulas that you can then later solve when you're actually, for instance, in a challenge response. For instance, you might essentially get value A back, and the service requires you to respond with 2 times A. This is not something that you can hard code in your exploit, but essentially you have to have the symbolic formula that depends on whatever the service sends you. And these kind of things we included as essentially including a solving engine in our exploits. And the shortest exploit that we actually had was essentially just making sure that one specific thing is set, and it ended up at only 226 lines of code. And one more thing is essentially the crack adder exploit, which essentially tried to mimic a specific exploit, essentially in a specific exploit from the past, which we ended up with 517 lines of C code. If you have looked at, I'm not sure if you have, but all of the challenges are actually open source. So DARPA made all of them open source after. And we were able to generate essentially 100% reliable exploits for the following challenges. And the rematch challenges, where the rematch challenge was essentially a service that existed in the past, in the last 20 years, for which there was an exploit that had somewhat devastating impact, for instance, SQL Slammer. And essentially, these kind of exploits we also discovered too, automatically without any human involvement. The different kind of vulnerabilities that essentially Mechanical Fish was able to find include primarily buffer overflows, buffer overreads, all these kind of things, but also, for instance, out-of-bounds writes, which it was able to then essentially use to exploit, for instance, vtable overflows. Looking specifically at essentially the statistics of the CVE, so the pwning statistics, how many flags have we captured, how many teams have other teams captured, how many challenge sets has a specific team found an exploit for, and how many essentially, both of that for 49 rounds and for all rounds. We included the 49 rounds because that's the cutoff date of Mayhem. So Mayhem ran into a problem where it's essentially stopped talking to the API. So it was running on old and outdated information at that point. And for instance, in the first 49 rounds, we essentially captured a total of 206 flags, where Mayhem, who won at the very end, captured 185, while the lowest team captured 20. And interestingly, so you can see that Mayhem with For All Secure pwned the most challenge stats by far in the first 49 rounds, and nobody knows what would have happened if it would have run another essentially 46 rounds, which then might have given essentially that it might have been able to pwn possibly 30 binaries. And on the patching side, CSDS did really well essentially in defending the challenge sets by round. So how many challenges that essentially they defended in each round. But Deep Red and us essentially did the best in not getting exploits for most challenge sets. So we might have taken longer for essentially than CSDS, for instance. CSDS was very quick in applying general patches that prevented a lot of exploits, but they will not be essentially able to patch more find more fine-grained bugs that required more in-depth patches where a generic patching strategy didn't work. There's some stupid bugs that we of course ran into because, well, testing as that is not our strength. There's one, for instance, which was network traffic synchronization. So one of our components tried to download all of the network traffic for all previous rounds, every round, instead of just downloading the one from the last round. That actually ended up in kind of a problem as soon as you start hitting like 20 rounds, because then you start to try to download gigabytes of data within like a 20-second interval. That doesn't really work as well. Then we also had a race condition in our submission logic to essentially, which forced us to resubmit and at specific boundaries of the round, which then means if you submit twice because of a race condition, you actually are hit twice by downtime, because you're first deploying in this round and you're having downtime the next round, and then the next round you're deploying again, and then you have downtime in the one after again. Another thing that we run into was really slow scheduling from Kubernetes. So Meister sometimes tried to schedule 2,000 to 3,000 jobs every minute, or essentially to at least shuffle them around. And Kubernetes was sometimes as slow as 10, at most 20 different containers or jobs per second. And if you try to do that, the math there, that doesn't necessarily work out. So after the minute, you essentially have like 800 jobs left that you want to schedule. These were some of the things that we essentially really had problems with, and none of them we have figured out so far. We think this is going to walk into a specific direction, and that's essentially human augmentation. We think that exploiting everything by machine is not going to work, but everything exploiting by human is still very labor intensive. There are a lot of things that essentially, if you start to essentially exploit something, there are a lot of things that a machine can help you with. And that's essentially exactly what we did for the DEF CON CTF that followed the CyberGrand challenge. And it was really interesting to see, our cyber reasoning system helped in essentially getting exploits. So what we did, essentially, we pointed our cyber reasoning system, Mechanical Fish, to a specific point in the code. Essentially, we want to reach there, we want to go there. And then essentially we came up with an input to essentially go there, and as soon as this happened, the CRS took over and essentially generated a ROP chain to get a fully fledged exploit. And then essentially also, since we generated adversarial patches including backdoors, it was really interesting to see that some of the top teams actually took our patched binaries without understanding that there was a backdoor in there, or ignoring it because it might still be a patch for them because they're suddenly only being hit by us and not possibly hit by the other teams. It was really interesting to see how they deployed our backdoor and then giving us access to their flags. One other thing is API incompatibilities are really brutal. So since the DARPA CyberGrand Challenge people did not open source their competition framework before, obviously because they didn't want to get it attacked during the competition, we ran, I think, into like probably a day and a half of just trying to fix little API incompatibilities, even though the DEF CON CTF and DARPA CyberGrand Challenge are running the same API. We have open sourced all of the code that we wrote for the DARPA CyberGrand Challenge. So all of the different components that we have are open sourced. That includes Meister, Ambassador, Scriba, Farnsworth, Rex, ColorGuard, NetworkDude. All of them are open source on GitHub. All of them are licensed under BSD license. So you can take them and play around with it. There's Ansible scripts to essentially deploy everything. Some of them might not work on your infrastructure readily because they're really tailored to the CTF, the CGC infrastructure that they gave us. But if you essentially open an issue there, we can easily essentially look into that and fix it. Of course, this is like a huge effort, not only on our side, but also essentially a huge effort from other open source components that we relied on. And we just want to give them a huge shout out. These are both operating systems going down to essentially containerization, to essentially scheduling on large clusters, and of course, obviously, AFL. With that, I would like to thank you for your attention. Please stay in touch. You can follow us on Twitter, the full Shellphish team, or everyone individually. If you are a student and you're looking for an internship or a master's thesis, or you just want to consider doing a PhD in the US, feel free to come and talk to me. Our lab loves to take people there for essentially come for 3 to 6 months, do a project, and then decide possibly move on with their life. Thank you.
We might have time for one single question, but I understand it's late, so maybe not. You can always catch Kevin. You're here the next few days?
Yes.
All right, so catch him the next few days and go get ready to hop on your buses. There's a bus for the speakers, there's a bus for the non-speakers. So if you want to go to the city, feel free to get on the bus. And thank you for today. And thank you, Kevin.